So I'm hearing a lot of people asking why areas that are not near fault lines can still get earthquakes. Now, every country in the world actually sits on a bunch of tectonic plates.
Beneath the Pacific Ocean, Earth's largest tectonic plate is constantly moving, sliding, and sinking under others. Scientists say this slow motion builds enormous pressure along faults and deep ocean trenches. When that pressure is released, powerful earthquakes follow. The movement isn't new, but new data shows how active it truly is. What does this mean for the future? What the Pacific Plate really is? The Pacific Plate is the largest tectonic plate on Earth. It covers more than 1/3 of the planet's surface and stretches from the western edge of North America across the Pacific Ocean to Asia and Oceania. Unlike continental plates, it is made almost entirely of dense, oceanic crust, which plays a major role in how it behaves beneath the planet's surface. Tectonic plates are massive slabs of Earth's outer shell that float on a softer layer beneath them, called the mantle. They do not move suddenly or violently on their own. Instead, they shift slowly, at about the speed your fingernails grow. The Pacific Plate is one of the fastest, moving several centimeters each year in a northwest direction. Because it is so dense, the Pacific Plate does not easily ride over other plates. Instead, it is often forced downward beneath them in a process called subduction. This is why deep ocean trenches, powerful earthquakes, and long chains of volcanoes surround much of the Pacific Ocean. The Ring of Fire explained. The Ring of Fire is a vast zone of seismic and volcanic activity that wraps around the edges of the Pacific Ocean. It stretches for about 40,000 kilometers, passing along the west coasts of North and South America, up through Alaska, across Japan, the Philippines, Indonesia, and down toward New Zealand. This region contains more than 70% of the world's active volcanoes and produces most of Earth's largest earthquakes. The name Ring of Fire may sound dramatic, but it describes a well-studied geological pattern. The Pacific Plate is surrounded by several other tectonic plates, including the North American, South American, Eurasian, Philippine Sea, and Indo-Australian plates. Where these plates meet, powerful geological forces are at work. Many of these boundaries are subduction zones, where the dense Pacific Plate is slowly forced beneath neighboring plates. As the Pacific Plate moves downward, it does not slide smoothly. The edges of the plates often become locked together by friction. While they remain stuck, the plate continues to move, causing pressure to build deep underground. This stress can accumulate for decades, or even centuries, without any visible signs at the surface. When the locked section finally breaks free, the stored energy is released suddenly, producing strong earthquakes. This same process also explains the chain of volcanoes that outline the Ring of Fire. As the Pacific Plate sinks deeper into the mantle, it heats up and releases water and other fluids trapped within the rock. These fluids rise into the hotter mantle above, lowering the melting point of the surrounding material. Over time, magma forms and slowly rises toward the surface. When it breaks through, volcanic eruptions occur, often in long, curved lines that mirror the edges of the plate below. Countries such as Japan, Chile, Indonesia, and Alaska sit directly above these active plate boundaries. Earthquakes in these regions are not signs of sudden change or instability. They are the expected result of ongoing plate movement that has shaped coastlines, mountains, and ocean trenches over millions of years. The Ring of Fire is not a signal of Earth entering a dangerous new phase. It is a reminder that the planet is constantly moving, reshaping itself through slow but powerful forces beneath the surface. Subduction, where the real pressure builds. Subduction is one of the most powerful processes shaping the Pacific Plate and the earthquakes linked to it. It occurs when one tectonic plate is forced beneath another and sinks into the mantle below. Because the Pacific Plate is made of dense oceanic crust, it is especially prone to subduction along its edges. This is why many of the world's deepest ocean trenches and strongest earthquakes are found around the Pacific. At subduction zones, plate movement is not smooth or constant. The descending plate and the overriding plate often become locked together at their boundaries. Even though the Pacific Plate continues to move, the locked section resists motion. Over time, enormous stress builds along the fault line. This stress is invisible at the surface, but grows steadily deep underground. The most dangerous faults in these regions are called megathrust faults. These faults form where two massive plates meet over a wide area. Because of their size, megathrust faults are capable of producing the largest earthquakes on Earth. When they finally slip, the sudden release of energy can cause intense ground shaking over vast distances and, in some cases, trigger tsunamis. Subduction earthquakes do not happen on a predictable schedule. Some faults may release stress through smaller, frequent earthquakes, while others remain locked for centuries before producing a single, massive event. This long silence can be misleading. A quiet fault is not a safe fault. In many cases, the absence of earthquakes means stress is continuing to build. Scientists closely study subduction zones because they pose the greatest risk to coastal regions. By analyzing past earthquakes, seafloor deformation, and plate movement, researchers can estimate how much strain has accumulated along a fault. While this does not allow them to predict exact timing, it helps identify which regions are more likely to experience large earthquakes in the future. Subduction is not a sign that the Pacific Plate is failing or breaking apart. It is a natural consequence of plate tectonics. The same process that caused destructive earthquakes also drives the recycling of Earth's crust, shaping the planet over millions of years. Deep ocean ridges and fracture zones. While subduction zones mark where the Pacific Plate is being pushed downward, other parts of the plate tell a very different story. Across the floor of the Pacific Ocean lie long underwater mountain chains known as mid-ocean ridges. These ridges are places where tectonic plates are slowly pulling apart, allowing molten rock from deep within the Earth to rise and create a new oceanic crust. One of the most important of these features is the East Pacific Rise, one of the fastest spreading ridges on the planet. At mid-ocean ridges, the movement is gradual and steady. As the plates separate, magma rises, cools, and hardens, forming fresh seafloor. This process does not involve sudden, violent earthquakes. Instead, it produces frequent but relatively small tremors as the crust adjusts to constant motion. These earthquakes are rarely felt by people because they occur far beneath the ocean's surface and release far less energy than those at subduction zones. Connecting segments of these ridges are fracture zones and transform faults. Unlike subduction zones or spreading ridges, transform faults are places where plates slide horizontally past one another. The most famous example on land is the San Andreas Fault, but similar faults cut across the Pacific seafloor for thousands of kilometers. Along these faults, stress builds as the plates grind past each other, sometimes producing sharp, shallow earthquakes. Fracture zones can appear like cracks or breaks when viewed on maps of the ocean floor, but they do not mean the Pacific Plate is splitting apart in a dangerous way. They are natural features formed as the plate grows and moves over time. These zones help accommodate differences in plate speed and direction, allowing the crust to adjust without tearing itself apart. Together, mid-ocean ridges and fracture zones show that the Pacific Plate is constantly being created, reshaped, and recycled. New crust forms at ridges, travels across the ocean basin, and is eventually destroyed at subduction zones. This slow cycle explains why the Pacific Plate is both dynamic and stable. The cracking and shifting seen beneath the ocean are not signs of collapse. They are essential parts of the system that has governed Earth's surface for hundreds of millions of years. What scientists can measure. Today, modern technology has transformed how scientists study the Pacific Plate and the earthquakes linked to it. In the past, researchers relied mainly on surface observations and historical records. Today, they can measure plate movement with remarkable precision, even in the most remote parts of the ocean. Seismographs are one of the most important tools in earthquake science. These instruments detect vibrations in the ground caused by earthquakes, from large destructive events to tiny tremors that people never feel. Global networks of seismographs allow scientists to map where earthquakes occur, how deep they are, and how energy moves through the Earth. This information helps researchers identify active fault zones and understand how stress is being released over time. Another key tool is GPS technology. High-precision GPS stations, placed on land and on the seafloor, measure plate movement in millimeters per year. These measurements show exactly how fast the Pacific Plate is moving and in which direction. By comparing GPS data over many years, scientists can see where plates are smoothly sliding and where they are locked, storing energy that could later be released in earthquakes. In the ocean, scientists use specialized instruments such as ocean bottom seismometers and pressure sensors. These devices sit on the seafloor and record seismic activity that would otherwise go unnoticed. Some sensors are part of tsunami warning systems, designed to detect sudden changes in sea level after large undersea earthquakes. This data can provide critical minutes of warning for coastal communities. Despite these advances, there are clear limits to what science can do. Scientists cannot predict the exact time, location, or size of future earthquakes. The Earth's crust is too complex, and stress does not build or release in perfectly regular ways. What scientists can do is assess risk. By combining seismic records, GPS data, and geological studies, they can estimate which regions are more likely to experience strong earthquakes over long periods. This growing body of data does not suggest that the Pacific Plate is becoming unstable. Instead, it confirms what geologists have long known. The plate is moving steadily, and stress builds and releases as part of a natural cycle. Better measurement has not made the Earth more dangerous. It has simply made its hidden processes easier to see and understand. Why earthquakes seem more frequent? If you follow news about earthquakes, it can feel as though the Pacific region is experiencing more tremors than ever before. In reality, the Earth itself is not suddenly shaking more often. What has changed is our ability to detect, record, and report seismic activity. Advances in technology and monitoring have made even the smallest earthquakes visible to scientists and often to the public. One key factor is the global network of seismographs. Today, thousands of sensitive instruments around the world can detect earthquakes that are far too small for humans to notice. Even tremors occurring deep beneath the ocean floor are now recorded. Decades ago, these events would have gone completely unnoticed. With more earthquakes being logged, the apparent frequency naturally appears higher, even though the overall seismic activity of the planet remains consistent over time. Another factor is population growth and media coverage. More people live near tectonic plate boundaries today than in the past, and most have access to real-time news or social media. Every earthquake, even minor ones, can quickly become widely reported. When a tremor is widely shared online, it can create the impression that earthquakes are happening more often, even if the actual rate of significant events has not increased. Clusters of earthquakes can also draw attention. Sometimes, a region experiences a series of moderate tremors over a short period. While these clusters may feel alarming, they are often part of natural tectonic processes. Stress is constantly building and releasing along faults, and small earthquakes can sometimes occur in succession as part of this cycle. Scientists also distinguish between short-term fluctuations and long-term trends. Data collected over centuries show that earthquake activity varies locally and regionally, but does not indicate a sudden global increase. What is new is our ability to track patterns, measure strain, and identify which areas are accumulating stress more rapidly. This knowledge improves early warning systems and disaster preparedness, giving communities a better chance to respond when a large earthquake occurs. Ultimately, earthquakes may feel more frequent because of technology, population density, and media attention, but the Pacific Plate continues to behave as it has for millions of years. The shaking we experience is a natural outcome of slow, ongoing movement beneath the Earth's surface. By understanding these processes, scientists can focus on where the greatest risks lie, rather than being misled by perception or isolated clusters of activity. The largest earthquakes linked to the Pacific Plate. Throughout history, some of the most powerful earthquakes on Earth have been directly linked to the movement of the Pacific Plate. These events provide a clear view of how stress builds and releases along plate boundaries, and they offer valuable lessons for scientists and communities alike. One of the most significant was the 1960 Chile earthquake, the largest ever recorded, with a magnitude of 9.5. This megathrust earthquake occurred along the boundary where the Pacific Plate is being forced beneath the South American plate. The sudden release of stress caused massive shaking, widespread destruction, and tsunamis that traveled across the Pacific Ocean. Despite occurring over 6 decades ago, the Chilean earthquake remains a key reference point for understanding how megathrust faults operate. Another major event was the 1964 Alaska earthquake, which measured 90.2 in magnitude. The Pacific Plate's movement beneath the North American plate caused this massive earthquake, one of the strongest ever recorded in the Northern Hemisphere. The event reshaped landscapes, triggering landslides, tsunamis, and ground subsidence. It highlighted how subduction zones along the Ring of Fire can produce catastrophic shaking, even in relatively sparsely populated areas. The 2011 Tohoku earthquake in Japan, at magnitude 19.1 was another stark reminder of the power of the Pacific Plate. The Pacific Plate subducting beneath the Okhotsk microplate caused sudden, violent motion along a megathrust fault. The resulting tsunami led to thousands of deaths and severe damage, including the Fukushima nuclear disaster. Scientists have studied this event extensively to better understand earthquake mechanics, tsunami generation, and disaster preparedness. While these are the largest, numerous smaller but destructive earthquakes have also shaped human history around the Pacific. Regions like Indonesia, the Philippines, and New Zealand regularly experience magnitude 6 to 8 earthquakes along subduction zones and fracture lines. Each event reinforces the pattern. Stress accumulates slowly, often for decades, before being released in sudden, intense shaking. From these examples, several lessons emerge. Large earthquakes are concentrated along subduction zones, where one plate slides beneath another. They can produce tsunamis that travel thousands of kilometers across oceans. The interval between massive earthquakes on a single fault can span decades or centuries, meaning that a quiet period does not indicate safety. Ultimately, the largest earthquakes linked to the Pacific Plate are not signs of instability or collapse. They are natural outcomes of long-term tectonic movement. Studying these events allows scientists to better assess risk, improve early warning systems, and help communities prepare for future earthquakes. The Pacific Plate will continue moving, building, and releasing stress, shaping both the ocean floor and human history in profound ways. Predicting earthquakes and what it means for the future. Despite all the data scientists collect, predicting the exact time and location of an earthquake remains impossible. The Earth's crust is a complex system, and stress does not build or release in regular, predictable patterns. While we can identify regions where large earthquakes are more likely, we cannot know precisely when the next major event will strike. This uncertainty is a natural part of living on a dynamic planet. Instead of prediction, scientists focus on forecasting and risk assessment. By studying past earthquakes, measuring plate movement with GPS, and analyzing geological features, they can estimate which areas have accumulated the most stress. This allows governments and communities to prepare for the possibility of large earthquakes. Early warning systems are another tool. In some regions, sensors can detect initial tremors and send alerts seconds or minutes before shaking reaches populated areas. Scientists also study fracture zones, long cracks in the ocean floor, where plates slide past one another. While these zones do not break the Pacific Plate, they help accommodate differences in motion and relieve stress gradually. Similarly, early warning systems provide seconds to a minute of notice for shaking, depending on distance from the epicenter, for tsunamis generated by large, undersea quakes. Warnings can extend for hours, giving coastal communities time to evacuate. Understanding these processes allows scientists to refine risk assessments and preparedness strategies without overestimating danger. While brief, these warnings can save lives by giving people time to take cover or stop trains, industrial machinery, and other hazardous operations. Looking ahead, the Pacific Plate will continue its slow, steady movement. Subduction will carry the plate beneath neighboring plates. Mid-ocean ridges will produce new crust, and fracture zones will adjust the plate's shape. This is a cycle that has shaped the Earth for hundreds of millions of years. Large earthquakes will continue to occur along subduction zones and other active boundaries, but these events are part of a predictable geological process rather than a sudden or unprecedented crisis. For people living near the Pacific Plate, understanding these processes is crucial. Knowledge reduces fear. Preparedness, building codes, and community planning make a far greater difference in safety than worrying about unpredictable big quakes. Scientific research continues to refine our understanding of plate behavior, stress accumulation, and seismic hazards, improving our ability to respond when earthquakes happen. The Earth is a living system. The Pacific Plate is moving, reshaping the seafloor, creating mountains and trenches and generating the earthquakes that remind us of our planet's power. These forces are neither new nor accelerating unnaturally. They are part of the long-term rhythm of plate tectonics. By observing, measuring, and preparing, humans can coexist with these forces, reducing risk while appreciating the processes that have shaped the Pacific region for millions of years. The question is not whether earthquakes will happen, but how we respond when they do.